So for this module, we'll be learning about iterated integrals. So the objectives are to evaluate an iterated integral and to use an iterated integral to find the area of a plane region. So this one we have already learned how to solve for an area, but using a single integral. Now we will be using multiple integrals. So that's why you call it iterated integral. So when you look at this one, function of xy with respect to x dx. So you will evaluate it with respect to x. And then if for example, you're given something like this, function of xy with respect to y dy. So it's with respect to y. So you can see naman with respect to what variable. So the independent or the variable of integration for the first one is x. For the second one, it's y. So you know how to integrate this one. But then the problem, guys, look at this. Usually, when we integrate, it's either with respect to y or with respect to x, right? But the problem now here is, how do you integrate this? This is both with respect this one, you have both x and y variables in one problem. But then look at the variable of integration. It says here that in the variable of integration, it's with respect to y. So that means if it is with respect to y, every other letter that appears in here should be considered as a constant. So how do we solve this? Considering x to be constant and integrating with respect to y, you have this one. So the x and the 2 should be constant. So that means what we will integrate now is simply y. This one would be y squared over 2. But then since it has 2 in front, it cancels. It becomes xy squared. Here, 3, let's move it out. It becomes y cubed over 3. But then since there's 3 in front, it's just y cubed. So in here, this is the integral. Now, you would like to evaluate it from 1 up to x. Most of the question will be, where do we plug in the limits? You have just evaluated it with respect to y, so that means every letter y or every variable y there, that's where you'll plug in the limits. So here, that's going to be x and then x squared, right? And then here, x cubed minus x times 1 plus 1. So you'll end up with 2x cubed minus x minus 1. Let's go to another example. So in this case, it's more than one integration kasi you'll have this multiple integrals already. So first, we'll start with the inside going outside. So we'll start with y followed by x. But this one, this is actually the problem I gave you earlier. It's this. So I can say that the inside part can be replaced by the previous answer. And then I'll integrate this now simply by integrating it with respect to x. So this one, it's basically simple integration. And then after that, you can solve for that. I'll give you more examples, don't worry. So the integral in example 2 is what you call the iterated or multiple integral. So iterated integrals are usually written as function of xy with respect to y and then with respect to x. So the first limits are for letter y. The next limits or the outer limits are for letter x. In this case, it's also a function of xy, but this one, you start with x followed by y. So it says here, the inside limits of integration can be variable with respect to the outer variable of integration. However, the outside limits of integration must be the constants. So the first limits can be variables, but the last limits or the outer should be constants. So after performing the inside, you should obtain a standard definite integral. And the second integration produces what you call the constants or the final answers, the real numbers. All right. So in here, sometimes what you'll have is a figure. So for the but then for this one, this just basically states the regions or the boundaries at which the shaded portion lies. For example, you can see here the x, the region is valid for x greater than or equal to 1, but less than or equal to 2. So this is the x values. And then for the y should be greater than or equal to 1, this line, and this line, y equals x or less than or equal to x. So this slant line. So that would be the shaded portion. So you can say the region of the integration would be from the first part, we'll take it y, from y equals 1 up to y equals x, and then the last or the outer limits would be for the constants, x equals 1 up to x equals 2. So of course, for iterated integrals, it's not just double integrals. We also have what you call triple integrals. Here, guys, don't be scared when you see the R, when you see the Q, what do those mean? Let's go to the definitions first. If f is defined on a closed bounded region R in the xy plane, then the double integral of f over R is, so R is basically just a region. So this one is basically the function of xy, and then the differential of your area, because it's two integrals. So the area bounded is over that region R, provided that the limit exists. If the limit exists, then f is integrable over the said region. And then on the triple integral, if f is continuous over a bound solid region Q, then the triple integral of f over Q is given by this. So basically, this one would be a function of three variables. Typically, we just use x, y, z. It can be any other letter like f of w, x, and m. It's up to us. But of course, for illustrative purposes, it could be x, y, z. So with respect to v over that interval q, provided that the limit exists. And then this one would give us, since it's triple integral, this one would give us a volume. So I'll give you more examples now. For example, this one. As I said, if, for example, you start with respect to x and then with respect to y, the first one should be integrated the first one should be integrated with respect to x, having y as a constant. And then after you perform that, that's why in here you'll notice x is a function of y, because y would be the constant. After that, the second step would be integrating the outside. If you have triple integrals, just a reminder, first you will integrate with respect to y. But the thing is, you have three variables, x, y, and z. So if you're integrating with respect to y, the variables that are not declared in the first, so that means if it's with respect to y, x and z should be isolated. Y is a function of x and z, meaning here that x and z should be treated as constants. However, for the second integration, I will integrate now with respect to z. But of course, I'm finished integrating with y. So if I'm moving to z, what else haven't I integrated? It's x, right? So for the second integration, x would be the one that's left constant. That's why here, z is only a function of x, z is only a function of x. And then lastly, after after doing this, I'll integrate the outermost. But then there's no more constant because the constant are the real constants A and B. So let's just go to some examples. So in this case, that means we'll start doing the inside. For the inside, this is the first one. What would be the constant? This one is done with respect to x. Therefore, y is treated as a constant. And then next, I'll do the outermost or the outer integrals. This one, number 2, is with respect to y. Therefore, the constants are the real constants. So let's do the first integration. For the first one, some of you might say, sir, is it okay to just copy the inside first? It's okay. You can separate them. So 0 to 2y of x squared plus y squared dx. So here we have to take note that this is with respect to x and that y is treated as a constant. So there's no y there. So that's just y cubed over 3. This is purely a constant. So y squared times x. And then I am integrating it from 0 up to 2y. So again, just a reminder, where will I substitute 0 and 2y? I just integrated with respect to x. So that means I will plug in 0 and 2y in all the x's that I see. So that's 8y cubed over 3 plus y squared and 2y minus 0 plus 0. This is 8y cubed over 3 plus 2y cubed. So 3 times 2 is 6. So that means that's 14 over 3 y cubed. This would be the answer for the first integration. But then, is that the final answer? Not yet. Because I need to integrate this one a second time around. So, but then I will integrate now from 1 to 2, the answer, which is this one, now with respect to y, right? Because this one is with respect to y. So it's easy. 14 thirds is constant. I'll just bring it out. 1 to 2 y cubed dy. So 14 thirds y to the 4 over 4 from 1 to 2, 14 over 12. This one would be 16 minus 1. So 14 over 12, 15. So let's just cancel. 3 becomes 5. This becomes 4. And then we can cancel pa. That's 2. That's 7. So the answer is 35 over 2. So now this is your final answer. I'll give you more examples. Let's go to another example. In this case, you are integrating first with respect to y and then with respect to x. So with me, it would help, guys, if I write here, like for example, just sort of like a guideline. So I'll do this. So it's with respect to y, x is constant, and then lastly, this is number 2 is with respect to x. All right. So let's do the first integration. So for the first integration, I need to integrate only the inside portion. So that's 4 over xy dx. So again, which one is constant with respect to y? So that means x is your constant. All the x's are treated as constants. So I can do this. 4 over x is now my constant, I'm just left with dy over y, right? What's the integral of dy over y? I can just say that's ln y from 1 up to e to the x. So let's do this. 4 over x ln of e to the x minus ln of 1. This one would be, I'll just write it here on the side, 4 over x ln e minus 0. And this one, take note that that's equal to 1. So 4 over x times x is equal to 4. That's the answer for the first integration. Let's go now to the second integration. In the second integration, it's with respect to x. So let's rewrite the question, but then just the outer limits from -1 to 1. And then the answer for the inside one would just be 4. So it's easy to integrate 4. The answer is 4x from -1 up to 1, 1 minus -1. So that's 4 times 2. The answer is 8. So again, the first one, as I have said, just as a guide, okay, but then I'll just write it here. The first one would be with respect to y. So that means x is treated as a constant. And then the second one is already with respect to x. So let's do the first one with respect to y. I'll just rewrite the problem. Since there's an x cube, what I can do is I can move out the x cube and then integrating from x to x squared, the dy all over xy plus 4 quantity square. So for this one, let's try power formula. If u is xy plus 4, n is -2, what is du? Take note, this is with respect to y. And then you have said earlier that x is constant. So it's simply x dy plus 0. Kasi take note, x is a constant now. Pretend that's 4y. The integral of 4y, the differential of 4y is 4 dy. In this case, it's x dy. But the thing is, look, if the u is xy plus 4, the n is -2, the du should be x dy. So that means here, I would have to rewrite this. X squared. This one has to be an x dy. So the outside portion, hindi siya pwedeng buong x cube. It has to only be an x squared because I need one of the x's to be inside. I'll just make this yellow. I didn't notice this x dy. All over xy plus 4 squared. So from there, where I moved out all of the x cube, here it seems like I need one x inside. So let's borrow one of the x's, and then only x squared is found outside. So now let's integrate. This is already integrable. X squared, this would then be xy plus 4 raised to -1 all over -1 coming from x up to x squared. And then let's bring that in. Let's bring out the negative sign, and then that's x squared all over xy plus 4 from x to x squared, negative of x squared all over. Here it becomes x cubed plus 4 minus x squared all over x and x. So x squared plus 4 only. And then let's just distribute the negative sign. They will interchange so that let's start with a positive. This one. Now, we cannot integrate this yet for the second portion because for the second one, you would want to integrate it with respect to x. However, this one, you'll notice that. So yeah, let's rewrite that first. Um, with respect to x. So rewriting this would be from 0 to 2 of x squared all over x squared plus 4 minus x squared all over x cubed plus 4 dx. The thing is, for the first one, since they are equal in degree, I will have to do long division. X squared, and then here x squared plus 4, that's 1. This is x squared plus 4. So I can bring out negative 4. For the second one, I don't need to do anything with that. So this one, from 0 to 2, 1 minus 4 all over x squared plus 4 minus x squared all over x cubed plus 4 dx. Now let's try to look at how we can integrate this. For the first one, it's easy. It's simply a constant. For the second one, I don't need the 4. I can bring it out. It looks like an arctangent. For the third one, the power of the denominator is bigger than the numerator. So let's take that as the u. Maybe it's an ln. If the u is x cubed plus 4, the du would be 3x squared dx. So I need a 3. I need to bring out 1/3. Okay? So that is readily integrable now, all of them. This one would then be x minus 4 over 2 arctangent of x all over 2 minus 1/3 ln of x cubed plus 4 coming from 0 up to 2. So let's plug in first the 2 minus 2 arctangent of 1 minus 1/3 ln of 8 plus 4 is 12. So this is the first group minus 0 minus 2 arctangent of 0 minus 1/3 ln of 4. And then take note that arctangent of 0 is 0 already. So 2 minus arctangent of 1 is pi over 4. So that's 2 times pi over 4 minus 1/3 ln of 12 minus minus. So this is plus. Wait. Minus. And then minus. Tama. So plus ln of. Sorry. Plus 1/3 ln of 4. 1/3 ln of 4. So if you want, you can actually combine this. So when you combine this, for example, 2 minus this is pi over 2. If I bring out the 1/3, this becomes ln of 12 minus ln of 4. And then loss on logarithms, if we follow that, you can say minus pi over 2 minus 1/3 ln of 3. Because 12 divided by 4 is 3. So that's it. I'll give you another one. So in here, the first one is, of course, with respect to x, where y is constant. You might say a is constant. Yes, of course. All other letters except for x should be treated as a constant. So in this case, let's bring out the y integral from 0 to the square root of y squared plus a squared. It's just dx all over x squared plus y squared plus a squared. Okay? So since this is tama naman, no? So since in this case, what are the constants y and a? What can you uh recommend that we do since this one is a constant? You have to recall what's the form. The best form that's closest to what we have now is this. If you can recall, integral of du over u squared plus a squared is equal to 1 over a arctangent of u over a, right? So if I say that this one is actually dx all over x squared plus the square root of y squared plus a squared squared, right? From 0 up to y squared plus a squared square root. There's y. It's the same, right? I can say, oh, okay, that one pala is the same as when I write it in this form. So with this, it's taking the form of an arctangent. So the integral of an arctangent would be y 1 over a. The a now is, so in this case, the a now is, I'll just rewrite here, a is actually the square root of y squared plus a squared. The u is simply an x. There should be no problem with that. So 1 over a, this one is y squared plus a squared, arctangent of u over a, y squared plus a squared in here, coming from 0 up to y squared plus a squared square root. So let's just leave this as y all over the square root of y squared plus a squared. The first one would be arctangent of 1 minus arctan of 0. So that means, again, an arctangent of 1 is pi over 4. So I can say y over square root of y squared plus a squared times pi over 4 because that becomes 0. So we can go now to our second integration. For our second integration, it's with respect to y. So I'll just copy. The pi over 4 is constant. I'll just bring it out from 0 up to a square root of 3. And then I'll place in here the y over the square root of y squared plus a squared dy. So in this case, you can see that the denominator is a bit more complicated. So let's just assume u to be y squared plus a squared. And then n is negative 1/2. Let's assume this is power. Let's see if it works. The du would be 2y dy. So all the parts can be completed just by adding a 2 in front. And then I need to bring out 1/2 outside. So let's integrate. This one is just pi over 8. So this is power rule. So u to the n plus 1 all over n plus 1. So y squared plus a squared raised to 1/2 all over 1/2. So that's simply 2 square root of y squared plus a squared, coming from 0 to a square root of 3. So again, the question is, where are you going to plug in the a square root of 3 and the 0 to letter y? So that's pi over 4 square root of a squared. So 3a squared plus a squared minus square root of 0 plus a squared. So pi over 4, this becomes 4a squared square root. That's just 2a minus, this is a. So that's just a. So a pi over 4 is your final answer. So in here, there are more examples. As you can see, this one. So you can practice more. I won't be answering this anymore. This one is another problem where you have triple integrals. So that's a final example. So some more examples that I would like you to work on are these as part of your problem set. So another topic is this one, how we can apply the iterated integral or multiple integral in solving for areas of plane regions. So let's consider this one. The plane region R bounded by x from A up to B and y from function of x1 up to function of x2. So this one, the pink portion, how do we solve for the area using multiple integrals? So what I can do here is, first, in our basic solving, in solving for the area of this one, it's basically length of the element times the width of the element. So basically, function up minus function down. That's why you have this. And then the thickness is dx. But then in applying more than one integral, or basically here, a double integral, how can we solve this? So what we do is we use the same element, but instead of it just being length times width, we draw a small box there. Small box having a thickness of dx, having a height of dy. So what we will do here is that small red box, we would want this to be traveling up and down to fill the rectangle. When you travel up and down to fill the rectangle, you're traveling along the y. That's why the order of this one is dy. And then that blue rectangle travels from left up to right along the x. That's why the order is dy first. The square completes the rectangular element. And then the rectangular element would travel sideways to fill out the shaded pink portion along the x. Placing a representative rectangle in the region R helps determine both the order and the limits of integration. That's why we place the rectangles. So a vertical rectangles or implies the order dy dx with the inside limits of integration corresponding to the upper and lower bounds. This is what you call vertically simple. If it's a vertical element, this is called vertically simple. However, if you draw a horizontal element, look at the red portion, the red square. In order to have that rectangular horizontal element, you would fill out the red along this portion. So it would move along the X. And then once it's filled out completely, the blue will fill out the pink portion. So the order is it's X first, the inside, and then the rectangle would travel along the Y. That's why it's an order of dx dy. In this case, this is what you call horizontally simple. So it's based on a horizontal element. Vertically simple, the order is dy dx, and then this one it's dx dy. So those are the things that you have to remember. So let's try solving some examples. Here, find the area bounded by the curve y equals ln of x and the limits y equals 0 and x equals e. We have solved this before. I just copied this portion. So using this red element, the length is y, the width is dx, right? So basically, it touches the upper portion, which is y equals ln of x, and then that element touches the lower portion, which is y equals 0. That's why you have up minus down. Look here, the up is ln of x, the down is 0. And then the limits are for letter x. The limits in x are 1 up to e. So this one, there should be no problem for you to solve this in solving that one. Let's convert this to multiple integrals. I'll just copy the same graph. So copying the same graph here. So x equals e. And then the intersection, that's 1 comma 0. This is e 1. So the graph has an equation of y equals ln of x. Now we would want this to be the shaded portion, of course. We would want to solve this. If I use the same element, a vertical element, if I use the yellow element here as my rectangular element, but then as I said, I would like you to make it into double integral. So in this case, let's draw a square. Okay, so for that, we can say that this one is dy, the thickness is dx. So I would like this to have two integrals. So integral, integral. The first is in the order of y because the y moves up and down. Look, when the y moves up and down, what's the limit of the top? It touches y equals, it touches y equals ln of x. At the bottom, that red square touches y equals 0. Kasi this one is y equals 0. Now, after dy, I'll have my dx. For my dx, look at the yellow rectangle. Where does it travel? What x value up to what x value? Okay, so it travels from 1 up to e. Take note again, when you integrate this, you will integrate this one first, followed by the outer portion, right? So let's integrate the first one from 0 to ln of x dy. That means it's simply y from 0 to ln of x. The answer is simply ln of x minus 0 or ln of x. So this one would be the first. Now, going to the second integration, integral from 1 to e of ln of x dx. Now, for ln of x dx, you can't integrate it immediately. Remember, integration by parts. u would be ln of x, dv is dx. So this one is 1 over x dx, and then this one is simply x. So applying integration by parts in this case would be uv x ln of x minus the integral of v du. So x times 1 over x dx. Let's apply the limits later on. X ln of x minus, this one just cancels. So that's simply an x coming from 1 up to e. Therefore, this is e ln of e minus 1 ln of 1 minus 1. So e ln of e is simply e minus e minus 0 minus 1. So in this case, the answer is 1 square unit. Isn't it, guys, that above the answer was 1 square unit? It's exactly the same. Look, here the area is simply the integral from 1 to e of ln of x dx. When we applied this one, we came up with an answer of ln of x. And when we did the second integral, it came up with the same uh, expression for the area. Look, oh, 1 to e of ln of x dx is basically that one. Now, let's do the same problem, exactly the same problem. This is the same problem that we had. However, this one, we're using the horizontal element. Again, that's 1 square unit, just like the answer in the previous slide and in the previous slide as well. Because it's the same problem, but then I would like you to apply a horizontal element. So when we redraw that, basically this one is um e comma 1. This is 1 0. So this is the shaded portion. This is x equals e. This is y equals 0. But I want you now to give me a horizontal element. Horizontally simple. So I won't shade the yellow portion anymore. I'll just create a red square inside. So the red square has a thickness of dx, and then the yellow rectangle has a thickness of dy. So it would travel along the x first, the square travels along the x to complete the rectangle. And then the rectangle travels up and down along y, the rectangle, and your square. Your square travels sideways. So this is in the order of or in dx, and then the rectangle travels up and down. This is dy movement, right? So along the x, if I ask you, what would be the limits? The x travels from where to where? From the right side is x equals e. The inside portion is the graph. This is the graph of y equals ln of x, or x equals e to the y. So the right side portion that the square touches is x equals e. The left side is x equals e to the y. This one is e to the y up to e, and then the yellow portion, since it's moving up and down, the lowest y value that it reaches is 0, and then the highest value of y is y equals 1. So if I ask you to write this in terms of double integral, what would be the order? The order would be dx first, followed by dy. What would be the limits? Let's look at the dx limit that we have written here, from e to the y up to e, and then the dy limits are from 0 up to 1. So let's take the first integration. For the first integration, with respect to x, this one would be simply e to the y up to e of dx. So that's just x from e to the y up to e. So it's e minus e to the y. This is your answer for the first one. Now let's integrate it the second time around, but now with respect to y. So the integral from 0 to 1 of e minus e to the y dy, this one would just be e times y minus e to the y coming from 0 to 1, e times 1 minus e to the 1 minus e times 0 minus e to the 0. This is simply e minus e, 0 minus 1. So the answer is 1 square unit. Isn't it that this one, when you compare, look at this problem, integral from 0 to 1 of e minus e to the y dy, isn't that this problem? It's exactly the same problem, exactly the same answer. But then now we use a double integral, horizontally simple element. The other one, vertically simple element.